All right, so in this video, we're going to begin Unit 2, and we're going to talk about types of chemical bond, and we're going to talk a little bit about some properties of ionic solids and properties of alloys as well. But our focus is going to be on these three types of bond that hopefully you're already familiar with the idea that bonds can be classified as metallic, ionic, or covalent. The discussion of bond enthalpy, while it's included in the slides here, won't be included in this video because it's going to be covered later in the year. So first of all, let's talk about different types of chemical bonds. And the problem is there's no real simple and still complete way to define what a chemical bond is. It should make sense that a bond is a force that holds a group of atoms together and makes them function as a discrete unit. But there is not just one universal definition we can use. We need to think about it a little bit more organically. Um, it is true for all types of bond, however, that the energy of the system is going to be lower than if the separated atoms existed. In other words, a bond is always a more relaxed state for matter to be in, for a sample of matter to be in. Otherwise, the bond wouldn't form spontaneously. It is also a very, very, very important concept. Three varies that bond formation is exothermic. And we'll be coming back to this when we study thermochemistry and thermodynamics more carefully, but it is very important to remember that bond formation is exothermic. If you want to break a bond, then you're going to have to invest energy. However, when bonds are formed, energy is released. And that's because the system is going to a more relaxed state. So we'll keep coming back to that very important idea. But the three types of bond are ionic, covalent, and metallic. In introductory chemistry, we're often taught that ionic bonds are formed when a metal and nonmetal atom form a bond. And covalent is going to be formed always between nonmetal atoms and nonmetal atoms. This is a bit of an oversimplification, but it's an excellent start. Finally, metallic bonds are formed between metal atoms only, but it's important to note that if you have a substance that is made from only metal atoms, it's really not a compound. In other words, it's not a substance at all, it's a mixture. And that has to do with the fact that it's going to have variable composition. We can't write a chemical formula for an alloy the way we can write a chemical formula for a covalent compound or an ionic compound, because alloys can really combine metals in any ratio. So we're going to develop this distinction a little bit in this video as well. But let's focus on the way we're going to classify bond types first. We're going to start with metallic bonds, and um, hopefully this definition of a metallic bond as a sea of mobile valence electrons is familiar. Think about all of these purple spheres as representing, for instance, sodium atoms, nuclei, and these blue halos around each one being the valence electron in a sodium atom. It's like a game of hot potato. None of those sodium atoms really want that valence electron, so to speak. And so it's really able to be transferred very easily from one nucleus to another or from one atom to another. And that mobile sea of valence electrons, where we're really not sure where an electron owes its loyalty, so to speak, is why metals reflect light, and also why they conduct electricity is because those electrons are free to move. And that's very different from electrons that are locked up in a covalent bond or locked up in ions. So alloys, like I mentioned before, are going to be what results when we form metallic bonds. So if we understand the nature of metallic bonding, we can go on to think about what an alloy is. An alloy is a mixture. It's not a compound, and that is because alloys have variable composition. Water is always H2, H2O. But for instance, brass can be 60% copper and other percentages zinc and iron, or it can be 70% copper and other percentages zinc and iron. There are many different types of brass. So it's really not a compound. An alloy is really a mixture. Sometimes alloys will contain elements such as carbon, and they're still considered alloys. They're not compounds. And there's a famous example of carbon in an alloy called carbon steel. And it's a famous one because the nature of carbon steel is that it's an interstitial alloy instead of a substitutional alloy. And these are two terms that we want to be familiar with and are part of our objectives in this section. Alloys can be classified as either substitutional, which is going to result when the atoms that make them up have similar radii or sizes, atomic radii, and or ionic radii. And steel is an example of an interstitial alloy where you can see some atoms have a much smaller radius than others, and they can fit in the interstices or the in-between places. And when these interstices are occupied by small atoms, it makes it very difficult to deform the metal. If you imagine trying to slide those atoms past each other, that carbon atom, or whatever the interstitial atom is there, is going to prevent these from sliding very easily. That's why carbon steel is very strong. So this slide just formally defines substitutional alloys and interstitial alloys. In a substitutional alloy, the host metal atoms, whichever is the one that has a higher percent composition in the alloy, are simply replaced by other metal atoms of similar size, whereas an interstitial alloy, it's essentially the holes in between the closest packed metal ions that are occupied by smaller atoms like carbon. So there's a couple of topic questions that we can look at right now which cover the topics we've discussed so far. A good time to pause the video, but I'm going to move on and start talking about the next few things. We've talked about metallic bonding, and a good animation that I wanted to show about metallic bonding is given here. I don't know if you can see that easily, but you can see there is the nuclei of all of the metal atoms, and the valence electrons are just free to move around. And that's what metallic bonding looks like. By contrast, an ionic bond, and this isn't animating, so I'm going to just drag this in here, is very different. Here is the animation that shows an electron being transferred from a neutral sodium atom to a neutral chlorine atom. And after electron transfer occurs, we are talking now about a sodium cation and a chloride anion. And it is at that point that we have oppositely charged ions which attract each other. So the mechanism of an ionic bond is important to understand. Electron transfer occurs, and then oppositely charged ions attract each other. And the classic example there of sodium chloride, of course, is just one cation per one anion. If it were magnesium chloride, since there's always two electrons lost by magnesium in the formation of these bonds, the ratio is one magnesium to two chlorides. So it's almost always between a metal cation and a non-metal anion, and they're held together due to that opposites attract phenomenon. That's a Coulombic attraction, and we'll talk about that in a moment. This is a great way to picture an ionic compound, and it's important to know that ionic compounds are network structures. In other words, they don't really exist as discrete molecules. So we're never going to refer to a molecule of salt. Is this a molecule of salt? No. How about this? Is this a molecule of salt? No. How about this? Is this a molecule of salt? None of these are, because salt does not occur as molecules. Even if we get to the smallest formula unit of salt, that's still not a molecule of salt, because that's not how salt exists. It doesn't exist as discrete units, like here's one molecule, here's another. It exists as a never-ending structure, or a never-ending, kind of like a chain link fence, where every atom is connected to another atom infinitely in all directions. So that nature of the ionic lattice of an ionic compound is important to understand. Now, in this particular model, the model is showing sodium chloride, and you can see that the sodium atoms that are depicted there, which are the blue ones, are a little smaller than the chloride ions, and that should make sense based on what we know about ionic radii. But if we were modeling something like, instead of sodium chloride, sodium bromide, bromine is a much bigger atom. And also, bromine has a different number of protons in its nucleus than chlorine does. And so you can see, as we're talking about size of atoms, which is essentially the distance from valence electrons to the core, or related to that distance, and we're talking about the number of protons, this has got all of the components of a Coulomb's law kind of a problem or a way to think about ionic bonds. So Coulomb's law, we have discussed how it can be used to understand periodic trends, but it can also be used to understand the strength of an ionic bond, those attractions between cations and anions. If we have a larger charge, in other words, a +1 cation versus a +2 cation versus a +3 cation, we're going to have stronger interactions. And it should make sense based on Coulomb's law that the greater the number of protons or the greater the charge is, we're going to have a stronger force. If we have a smaller ion, then the distance between cation and anion is going to be smaller, and that's also going to lead to a stronger ionic bond. While we need to be careful that the ionic radius may be different than the atomic radius, we can usually make some pretty straightforward comparisons from one salt to another, for instance, from sodium chloride to sodium bromide. We're still going to be applying the same principles of Coulomb's law. So let's review how lattice energy, or in other words, the ionic bond strength, the energy in that crystal lattice, is related to the size of ions first. The first example in the top right is that of lithium chloride, and you can see lithium is such a small atom that that distance is very short, and we have a very, very strong bond. The bond is, or can be quantified as a lattice energy in kilojoules per mole. It would take a lot of energy to break that bond. A lot of energy is released when that bond is formed because of that short distance. As we get to larger and larger atoms, like those of sodium or potassium with the same anion, the distance becomes greater, and so the bond becomes weaker. And that's what lattice energy is showing here. A big ion is going to give you a weaker attraction between cation and anion, and the bond essentially can be thought of, the ionic bond, as weaker. Second of all, we want to talk about how lattice energy depends on ion charge. You can see both of these examples. The distance is about the same, 231 picometers, 239 picometers. Those are both about the same distance from center of the cation to center of the anion. But here we've got a +1 and a -1, and here we've got a +2 and a -2. That ion charge makes a difference, right? The larger charge means a stronger attraction and a stronger lattice energy. In other words, that's going to be a harder bond to break, and forming that bond will release a lot of energy. So I've talked a little bit about lattice energy, and I've kind of equated that with the strength of the bond. It's technically defined as the energy released when the solid crystal forms from separate ions in the gas state. So when bonds are formed, energy is released. And that's why those lattice energies were always given as negative numbers in kilojoules per mole, because bond formation is an exothermic process, right? It takes energy to break bonds, but energy is released when bonds are formed. And the larger the magnitude of the lattice energy, the stronger the bond is. So pausing there for a minute would be a good idea to make sure we understand those concepts. But there are some other properties of ionic compounds we should discuss while we're talking about ionic bonds. Typically, because it's a network structure, ionic compounds will have very high melting points, high boiling points. They'll be brittle, and they are crystalline. And it maybe makes sense why they're brittle. If we start to deform an ionic compound a little bit and try to bend it, then you'll see the first thing that's going to happen is cations will be lined up with cations. These magnets are preventing me from even doing it properly. And of course, that's a repulsive force. And so it's going to slip and break very easily. And that's why they're brittle. They'll tend to break. They won't change shape easily without breaking. The solubility of ionic compounds varies. That's going to be, again, about Coulombic attraction when we talk about the forces between this ion and water and compare it to the forces between this ion and other cations. So solubility of some ionic compounds varies. Like we know, sodium chloride is soluble, but silver chloride is very, very slightly soluble. It's really very insoluble. And that has to do with some of the Coulombic attraction principles we were talking about before. A couple of other points about properties of ionic compounds that we should remember from first year chem. Ionic compounds do not conduct electricity in the solid state. If you try to put some electrodes into salt, then you will not get electrons moving. And that's because the electrons are locked up in these ions. This one has gained an electron from sodium. This one has lost its electron. You're not getting those electrons moving. But when you start dissolving salt in water, then it conducts electricity. That solution conducts electricity. Why would that be? Because now you have charged particles, which are free to move. The cation and the anion are dissociated, floating around in water, and that allows electricity to flow. That gives a way for electrons to move from one electrode to another and complete the circuit. So it's important to know that ionic compounds conduct electricity in aqueous solution. If they are indeed soluble ionic compounds, then this is a great test for whether a substance is ionic. Finally, what about a liquid ionic compound? And we do not melt salt very easily. It's got a very high boiling point, like we mentioned before. But when ionic compounds melt, those ions are free to move. And that is actually the formal operational definition of an ionic compound, is that it will conduct electricity when it's in its molten state. So molten ionic compounds, because the ions are free to move around, will conduct electricity. Not a scenario you're likely to encounter in the lab, in the classroom very much, but it does come up in some other commercial and industrial applications. Here's a couple of topic questions that go over those concepts. So pause the video here to look at those. And when you're ready, we'll move on. We learned before, first of all, that the difference between ionic and covalent compounds is simply ionic is metal-nonmetal and covalent is nonmetal-nonmetal. Then a little bit later in the year, in first year chem, I explained that it isn't really that simple. It's really the difference in electronegativity which dictates whether a bond is ionic or covalent. But now we're taking it a step further and revealing that even that definition, or that way of distinguishing between ionic and covalent bonds, is not the only factor that chemists use in determining whether we should designate a bond as ionic or covalent. Generally, if it's a metal and a nonmetal, it's ionic. And generally, if it's nonmetals bonded to nonmetals, it's covalent. But ultimately, we need to look at the properties of the compound, and that's the best way to characterize the type of bonding. So this is a direct quote, but it's an explicit learning objective in our curriculum, that while the difference in electronegativity is often used to distinguish between ionic and covalent, it's really the properties of the compound that matter. So we already learned that ionic compounds have certain properties, like they tend to be brittle, they tend to have really high melting points, they tend to not conduct electricity in the solid state, but yes in the aqueous state, and yes in the liquid state. They'll conduct electricity in those states. So those are the properties that we're talking about. So what about covalent compounds? What are their properties? And also, what's the mechanism of a covalent bond? So first of all, covalent bonds are about sharing electrons, and there's an animation that I can show you in a moment to remind you about that. But we also want to remember that there are two types of covalent bonds: those where electrons are shared equally and those where electrons are shared unequally, nonpolar and polar. Here's the animation first that I was describing, and it's a little hard to see, but you can hopefully see that the two atoms start off as separate and then they join up, forming the bond. You could think of these as being two fluorine atoms or two chlorine atoms, which each have 7 valence electrons. Notice the core electrons aren't shown, just the valence electrons are shown. And when those electron clouds overlap or interpenetrate, then you can see the effect is that both atoms have a full valence shell, And it's really the attraction of one atom's nucleus to the electrons of another atom that is holding the bond together. So it's a mechanism that we want to take time to understand carefully, and we'll go into more detail about the mechanism soon. If both of these were the same element, like fluorine atoms or chlorine atoms, then those electrons that you see right around those bright lights would be shared equally. And that means we'd be talking about a nonpolar covalent bond, because the difference in electronegativity between two fluorine atoms is zero. If the difference in electronegativity between two atoms is very low, like maybe between oxygen and fluorine, then it's going to be considered a fairly nonpolar covalent bond. Or maybe between oxygen and nitrogen might be a better example. If the difference in electronegativity is high, then we consider that to be a polar covalent bond. And very occasionally, electronegativity values are provided to us in thinking about this problem. But we also may want to just be able to look at the periodic table and generalize about electronegativity based on the relative position of elements, knowing that electronegativity increases towards fluorine on the table. The larger the difference in electronegativity, the more polar the bond is. There's a great video which summarizes this, which I'm actually going to embed into this video, just because it does such a great job explaining the mechanism of covalent bonds. So I'm going to bring that over here and make the screen a little larger and show that right now.
A covalent bond consists of a pair of electrons shared by a pair of nuclei. Let's use this graph of potential energy versus the distance between the nuclei to see the change in energy as the distance decreases. We'll pay most attention to the bond in H2 and then look at Cl2 and larger halogens, defining two key bond parameters along the way. When the H atoms are far away from each other, we designate the energy as zero. As they move closer together, they attract each other more and more, and the energy decreases to a minimum. At this point, a stable hydrogen molecule is formed. If the nuclei come any closer, the energy increases rapidly as nuclear and electron repulsions take over. Now let's zoom in closer to see the overlapping atoms in more detail. When the atoms are far apart, they do not feel each other. But as they come closer, the nucleus of one atom attracts the electron cloud of the other, and the attraction draws the atoms still closer. Note the increasing electron density between them. Soon, the electron clouds interpenetrate. Attractions dominate, but repulsions between nuclei and between electrons become stronger. At the point of lowest energy, attractions just balance repulsions, and the two H atoms exist as an H2 molecule. The covalent bond is the mutual attraction between the nuclei and the electron pair. If the nuclei were to move closer, repulsions would outweigh attractions. The increase in potential energy would destabilize the system and the atoms would move apart again. In reality, the molecule vibrates, the atoms moving slightly farther and closer at the point of minimum energy. The bond length is the average distance. For H2, it is 74 picometers. The bond energy, the difference between the minimum energy and the starting point, is the energy needed to break a mole of H2 molecules into separate H atoms. For H2, it is 432 kilojoules. Now let's compare H2 with Cl2 and other halogen molecules. The much larger chlorine atoms reach the energy minimum and form a Cl2 molecule at a greater internuclear distance. Because the Cl nuclei are farther apart, it takes less energy to separate the atoms, thus a greater bond length and a smaller bond energy. Moving down group 7A, bromine is larger still. So we would expect an even greater bond length and smaller bond energy. And iodine, the largest of these halogens, continues the trend to longer, weaker bonds. Stepping back, we see that in each case, mutual attractions draw the atoms together and they form a covalent bond of specific length and energy. Specific length and energy.
So I wanted to pause on this part of the video for a moment because it's an important image to refer back to. This graph, which was explained in the video, is a really important one in our curriculum. The College Board just loves this graph, and we want to understand it well. You'll definitely see some questions on the exam about this way of representing the energy associated with a covalent bond. And we'll be studying the energy ideas a little bit more closely in thermodynamics, but you can see here where 0 is marked as just designated as where the atoms are so far away from each other that they really don't attract each other at all. But you'll notice that here there is a low energy state. In other words, that is the most relaxed state for these atoms to be in, an even lower state than when they're separated. And that's the only reason that any bond will form, is if it's a lower energy state than the separated atoms. Of course, as they get closer and closer together, they repel each other. And that's what this part of the graph represents. And in that video, you saw many different diatomic molecules compared. The fact that each of them have the trough of the graph, so to speak, is at a different depth is important. And the distance at which that trough is on the x-axis is important. So there's a lot of good thinking to do about that graph. We'll be practicing interpreting that graph quite a bit. When we're talking about polar versus nonpolar covalent bonds, the unequal sharing of electrons that characterizes a polar covalent bond is important to understand. It's going to result in a separation of charge, a lopsided distribution of charge in the molecule, and that gives the molecule often a lopsided shape. We're not going to be talking about molecular geometry today or in this unit, but we are going to talk about, bond polarity, which sometimes leads to molecular polarity. Not always, but sometimes will lead to molecular polarity. And of course, in this
When
case,
the atoms in a covalent bond
me,
have different
when there's only one bond, if it's a diatomic molecule, then of course a polar bond must lead to a polar molecule. So let's just talk about polarity for just a minute. The reason I opened this other video was because I wanted to briefly remind you what it looks like when a polar molecule is in a electric field. And this might be a good part of the video to start. You can see with the field off, the molecules are oriented in random directions, but the electric field on, they orient in a particular direction. And so polarity of bonds is, of course, rather important. And while we won't talk about polarity of molecules yet, where sometimes even though a bond is polar, the molecule is not, we should understand bond polarity for now. Bond polarity depends on electronegativity. And electronegativity, remember, is defined as the ability of an atom in a molecule to attract electrons to itself. So it's really about bonding. Electronegativity, of course, increases as we get closer to fluorine on the periodic table. So it increases across a period and it decreases down a group. And the electronegativity value for fluorine is designated as 4, which is the highest value. And for cesium and francium, the lowest would be 0.7. And there's a couple of different types of electronegativity scales that people use. The Pauling electronegativity scale is the most common. And again, occasionally electronegativity values are supplied to us in a question, and we're asked to evaluate, the degree of a bond's polarity. Bond polarity can actually be quantified and measured in units called debye, but we don't need to study how we would use vector addition to calculate the dipole moment of a molecule. or of a bond. And we're just going to need to know that dipole moments will be shown as arrows. The arrows point to the negative side of the molecule. With the tail of the arrow, often I will have a cross on it to show that's the positive end. So here's a molecule of hydrofluoric acid. Remember, this lowercase letter delta is indicating the side of the molecule there's a partial positive charge, and the lowercase delta minus here is showing the side of the molecule where there's a partial negative charge. Not a whole -1 charge, but just a slightly greater density of electrons. A dipole moment is a characteristic of a molecule that contains polar bonds, and not only do the bonds need to be polar, it needs to be an asymmetrical shape. So we're going to talk about whether a dipole is produced in a molecule in the next unit when we start talking about molecular geometry. But right now we're really just talking about bond dipoles. And we could talk about the dipole moment of a bond or the dipole moment of a molecule. A dipole moment is not a moment in time. It is just a force vector that characterizes electron density distribution. Only a few topics left in this video. One is that boundary between ionic and covalent bonds is kind of a gray area. All bonds have some degree of ionic character, and there are formal ways of calculating percent ionic character in a bond, which are, again, beyond the scope of our curriculum, but we do need to know that distinction between ionic and covalent is a bit of a gray area. And we are going to just assume that if it's more ionic in character than covalent in character, then we consider it ionic. That really depends on the properties of a compound. So here are the topic questions that correspond to the many ideas that have been included here. So a good time to pause the video and look at those. There's only about 2 more minutes left that I want to use to cover bond order. So bond order refers to the number of shared electrons between atoms. In other words, is it a single bond, is it a double bond, or is it a triple bond? If it's a single bond, the bond order is 1, and there are 2 electrons shared in that covalent bond. If it's a double bond, we say the bond order is 2, and so on. In an upcoming unit, we'll also learn that single bonds are called sigma bonds, and double bonds consist of 1 sigma and 1 pi bond. And similarly, triple bonds consist of 1 sigma and 2 pi bonds. And this is just a preview of those ideas because sigma and pi bonds are concepts that relate exactly to the bond order. If we're looking at single versus double versus triple bonds, we need to know that triple bonds are going to be stronger and shorter bonds than single bonds. And so as we go from single to double to triple, the bonds get shorter and shorter and they get stronger and stronger.